Chapter 11 Kinetic Theory of Gases, Section 11.4 Collisional Frequency between gas particles. Gas particles move in all directions and collide with each other frequently. Assuming there are n mole argon gas in a container with volume V and temperature T, how many collisions does one argon atom experience on average within a time interval delta T? To answer this question, we need to define a collision cylinder or collisional cylinder that encloses the traveling trajectory of one gas particle of interest. So in this figure, we will study the number of collisions this red sphere is about to experience. Assuming this red sphere is moving in the horizontal direction from left to right. Now we're gonna examine the other particles. We have a total of 12 particles over here. And now you can see we have 5 blue spheres and 7 green spheres. What's the difference? If you look at the blue spheres, their centers are within this cylinder in the dashed line. If you look at the green spheres, their centers are outside this cylinder. And why do we need to separate these two different kinds of spheres? One in blue, the other in green. Well, it's just because we're just imagine the traveling of the red sphere from left to right. And in this cylinder, we have a radius of 2r. And r is the radius of one gas particle. So from here to the center, that's r. And from here to here, that's r. Alright, so we draw a cylinder that encloses the trajectory of this moving particle. And this cylinder has a radius of 2r, where r is the radius of a single gas particle. Now what will happen is this. If we look at the trajectory of the red sphere, when it moves to this direction, alright, it's going to collide with this blue sphere, right? And assume this red sphere keeps moving, it's going to collide with this sphere. How do we know that? Well, it's just because the radius of this cylinder is 2r. And over here you can see this is more than r and this is r. The sum of this one and this one is more than 2r. So inevitably there's going to be a collision between the red sphere and the blue sphere. Same here. Same for this one. Again, you just need to imagine this red sphere is moving to here. Alright? Now there's an overlap between the red sphere and blue sphere. That indicates a collision. And same here. But if you look at the green ones, well, this one will not collide with this one. So let's say the red sphere is moving towards here. At this position, there's no collision between the green one and the red one. How about here? Well, it's closer, but still, you just mathematically compute the distance between the center of this red sphere, somewhere here, the green sphere, somewhere here. You can see the distance between these two centers are greater than 2r. That means this green sphere is too far away from the trajectory. So mathematically, if we find a particle with its center inside this collision cylinder, a collision may happen. If the center of a particle is outside the cylinder, no collisions. The average speed of a gas particle is this, the square root of 8 kVt over pi amp. We derived this in section 2. The average relative speed between two such particles is different. Assuming both particles are moving, they can move toward each other, they can move away from each other, there can be a orthogonal angle, 90 degrees. So on average, if we integrate all possible probabilities, the relative speed between two particles is the square root of 2 times the average speed. The length of the cylinder within time delta t is therefore square root of 2 times the average speed times delta t. Alright, so from here to here, that's the length of the cylinder. That's also the distance this red sphere is about to travel within time delta t. It's not just the speed of the relative of this red sphere. It's the relative speed relative to the other particles. So we need to have a correction here. Square root of 2. Among all gas particles, the ones with their centers inside the cylinder, so all those blue ones, will collide with the moving atom in red color. The radius of the cylinder is again 2r. That's just the sum of the radii of the two colliding particles. If we have only one type of particles, well, it's pretty simple. It's just 2r, 2 times the radius. Okay, later we'll see if we have two different types of particles. The radius of the cylinder is going to be the sum of the radius of type 1 plus the radius of type 2. We can also calculate the area of this cylinder, which is just pi d squared, and this d is just 2r. Alright, and this circular area of the collision cylinder is called collisional cross-section area, denoted by sigma. So sigma is pi d squared, and d in this case is 2r. Now what if you have two different types of gas particles? So this is type 1, and all other particles are type 2. Now the radius of the cylinder is r1 plus r2. The collisional cross-section area is sigma. Sigma equals pi times r1 plus r2 squared. Again, we just need to sum up the radii of these two types. And in this picture, assuming this yellow sphere, the smaller one is moving from left to right, it's about to collide with only 4 spheres. Alright, over here 5 spheres. Over here 4 spheres. And why is that? You can see this radius is smaller than the radius of the red sphere, and therefore we have a thinner cylinder. And then there are fewer particles with their centers inside this thinner cylinder. The smaller the cylinder, collisional cylinder, the fewer gas particles with a center inside the cylinder. Now the volume of the collision cylinder of a moving argon atom is the length of its traveling distance within a time period of delta t. So it's this, square root of 2 times the average speed times delta t. Again, the square root of 2 is placed here because we're talking about the relative speed between two gas particles. And over here, two identical atoms, such as two argon atoms, they have the same average speed. And if we integrate over all possible orientations, the two argon atoms can move towards each other, and then the relative speed is 2 times the average. They can move away from each other, right? And also they can move in the same direction, and they can move in orthogonal directions. So overall we have this as the average speed multiplied by delta t as the typical length of the collision cylinder. The bottom area, or the circular area, is pi d squared, and d is 2r. So we have this equation. Now we have the volume of the cylinder, which is just the length multiplied by the circular area. and the average speed is the square root of 8 kbt over pi m. So we have this expression for the volume of the cylinder. Now, why do we need the volume of this collision cylinder? Well, it's just because it is difficult to count the number of collisions, but it's easier to calculate the number of argon atoms with their centers inside the collision cylinder. How do we do that? Well, we just need to know the number density of the argon atoms in the entire container, and then multiply it by the volume of the cylinder, and that will give you the number of argon atoms with their centers inside the cylinder. We're assuming the homogeneous distribution of those argon atoms in space. Alright, so for example, if we have 1 million argon atoms within a 1 cubic meter container, and we can compute its density. It's 1 million per cubic meter. And then if you have a collision cylinder with a volume, for example, 10 to the power of negative 3 cubic meters, we know roughly the number of argon atoms in 10 to the power of negative 3 cubic meters is 1,000. It's going to be a million per cubic meter times 10 to the power of negative 3 cubic meter, and that's 1,000. And from the previous diagrams, you can see if a particle has its center inside the cylinder, there's going to be a collision between these two, between these two, between these two, between these two, between these two. If the center is outside the cylinder, no collisions. So really, we do not have to count the number of collisions. We just need to know the number of atoms inside the collision cylinder. That's simply the number density N over V multiplied by the volume of the cylinder. N is the total number of atoms in the container, V is the total volume of the gas container, N over V is the number density. So over here we have this as the volume of the cylinder, the length of the cylinder multiplied by the circular area, and then multiplied by the number density. All this is the number of collisions the moving gas particle will experience within a time period of delta t. Alright, so all this has a physical meaning. That's the number of collisions the moving argon atom experiences within delta t. It's the length of the cylinder times the circular area of the cylinder times the number density. Well, of course, the denser the gas is, the larger the gas particles are, or the faster the gas particles move, the more collisions will occur within that time period. So mostly we're talking about this. If N over V is larger, or if D is larger, or if the average speed is larger, and then we have more collisions within a given time period. And now on average, when there's only one type of gas particle, each particle on average undergoes this many collisions within the time interval delta t. And therefore we can compute the collisional frequency, denoted by lowercase c sub 11. C sub 11 means the collisional frequency experienced by one particle, and this 11 means type 1 and type 1 collision. So we have the number of collisions within delta t divided by delta t, and that's the frequency. And over here you can see it's square root of 2 times the average speed times the collisional cross-section area times the number density. Again, 11 is not 11, it's type 1 collision. Later we will use Z sub 12 for type 1 type 2 collision. Again, the average speed is V sub AVE, the square root of 2 is to take the relative average speed into account. Pi d squared is the collisional cross-section area denoted by sigma. And in general, larger atoms have a larger sigma. But if we really analyze the collisional frequency between argon and helium, yes, argon is larger. The collisional cross-section area of argon is 1.7 times that of helium. So over here, this pi d squared for argon is larger. But the average speed of helium is larger than argon. So this one is 3.2 times of argon. So overall, if we consider both sigma and the average speed, we'll see very often larger atoms have a lower collisional frequency. Smaller atoms often have a larger collisional frequency. Assuming this N over V is the same, we can estimate N over V given the temperature and pressure of the gas using the ideal gas law. N is the number of moles times Avogadro constant, and the number of moles over volume of the container is just P over RT. So the number density is the pressure times the Avogadro constant over RT. Now let's look at the collisions between two different types of gas particles. Let's focus on this yellow sphere. It's going to move in this direction. We drew a collisional cylinder with a radius of R1 plus R2. R1 is the radius of the yellow sphere. R2 is the radius of the blue sphere and green spheres. So we can see these four blue spheres have their centers inside the cylinder. So the yellow sphere is about to collide with the blue ones, but not the green ones, because the centers of the green spheres are outside the collision cylinder. So we can write out the collisional frequency for this this yellow particle. It's the average speed times the collisional cross-section area, pi d squared, times the number density of type 2 particles. Alright, so again, we just need to have this volume and then the number density of type 2 particles. D12 is this radius of the cylinder. It's R1 plus R2. V12 is the average speed. So this relative speed is the speed of R1 relative to the speed of type 2 particles. So V12 is equal to the square root of V1 squared plus V2 squared. To memorize this equation, you kind of just assume V1 and V2 are orthogonal to each other, and you just need to sum up two vectors that are orthogonal to each other, and it's this equation. What if a gas particle is not spherical? How can we get the radius? Well, we can still estimate the radius of a non-spherical gas particle. For example, water is not spherical, oxygen 2 molecule is not spherical, but in this case we can simply define R to be the radius of the smallest sphere that can fully contain the non-spherical particle. So whatever sphere that can contain this O2 molecule, its radius is roughly 2 times the radius of an oxygen atom. Alright, so if you have a molecule with a non-spherical shape, you just need to find 2 points on the molecule that are the farthest away from each other, and that will be the diameter of the sphere that can contain this entire molecule. And again, V12 is the relative speed, And after we put a bar on top, this is the average relative speed. That's the square root of v1 squared plus v2 squared. Both are average speed. And the collisional frequency between type 1 and type 2 particles can be calculated this way. It's n1 times the lowercase c12. So the lowercase c12 is the collisional frequency for one type 1 particle. But we have n1 such particles, so we simply just use this n1, the number of type 1 particles, multiplied by the number of collisions experienced by each type 1 particle within a unit time. So we get this equation. But this equation is not very useful. This is an extensive property that changes with the size of the system. So for convenience, we want to have a intensive property that does not depend on the size of the system. So really we define this uppercase C12, which is the total collisional frequency between all type 1 molecules and all type 2 molecules, and then divided by volume, so per unit volume here. And this way we have an intensive property over here. And this can be written as the average relative speed times the collision cross-sectional area times the number density of type 1 and the number density of type 2 molecules. N1 over V is the lowercase n1 over V times the Avogadro constant. And the lowercase n1 over V is just P1 over RT, based on ideal gas law. Similarly, N2 over V is P2 over RT times Avogadro constant. And therefore, if we are given the temperature, the partial pressure of type 1 particles, the partial pressure of type 2 particles, we will be able to get this uppercase C12. The physical meaning of this is the total number of collisions between all type 1 particles and all type 2 particles per unit time, per unit volume. So it's here. And the expression is this. Again, it's the same as this one. It's just N1 over V is P1 times Avogadro constant over RT. Again, the total collisional frequency per unit volume between type 1 and type 2 particles can be expressed this way. The average relative speed times the collision cross-section area times the number density of type 1 and number density of type 2. And this is the formula for the average relative speed. Over here, V1 is 8 kBt over pi m1, V2 is 8 kBt over pi m2. We combine this, we get the square root of 8 kBt over pi mu. And mu is the reduced mass of two particles. And you can tell 1 over m1 plus 1 over m2 is just 1 over mu. This is how mu is defined. Mu is smaller than m1, mu is smaller than m2. Type 1 particles also collide with each other. So there is type 1 collision. The equation is like this. The uppercase Z11 is 1/2 of the number density of type 1 times lowercase c11. Why do we need this 1/2? Well, it's just because when two particles of type 1 collide, without having this 1/2, we will count this collision twice for both particles. So we need this 1/2 factor to avoid double counting. Similarly, the uppercase C22 is 1/2 of the average relative speed between type 2 particles, multiplied by the collisional cross-section area, multiplied by the number density of type 2, and then again the number density of type 2. So the total number of collisions is actually all those together, uppercase Z12, uppercase Z11, uppercase Z22. So that's the total number of collisions per unit time per unit volume, or the total collisional frequency per unit volume. For bimolecular reactions between type 1 and type 2 particles, we don't care about Z11 or Z22, we care about Z12, because only the collisions between type 1 and type 2 result in a chemical reaction. So the reaction rate should be proportional to this uppercase Z12. And you can see the reaction rate should be proportional to the number density of type 1, the number density of type 2, the average relative speed, and how large those molecules are. For the bimolecular reaction between type 1 and type 2 particles, the reaction rate R is proportional to uppercase Z12. Uppercase Z12 is the collisional frequency between all type 1 and all type 2 per unit volume. And the expression is this. Not all collisions result in a successful reaction because we need to consider two more factors: the energy factor and the entropy factor. So first, the energy factor. The probability of the colliding particles having enough energy to overcome the reaction barrier has to be considered, and that's the energy factor. And the probability can be computed using this equation: e to the power of negative activation energy over RT. T is the temperature, E sub A is the activation energy, R is the ideal gas constant. So we need this factor in the reaction rate. The second one is the probability of the particle colliding at the right angle, and it's the so-called orientation factor. And this orientation factor is denoted by F. F is unitless, and it's often much smaller than 1. Loosely speaking, F includes the entropic effect, so we often call that entropy factor as well. We have the energy factor, we have the entropy factor. Now, including both the energy and the orientation factor, we have this expression. We have F as the orientation factor, e to the power of negative activation energy over RT as the energy factor. Uppercase Z12 is the collisional frequency between all type 1 and all type 2 particles per unit volume, and that's the reaction rate. I just somehow expanded this Z12 as the average relative speed times the collisional cross-section area times the number densities of type 1 and type 2. We can also express this number density in terms of concentration. So this N1 over V is the lowercase n1 over V times Avogadro constant. That's just the concentration of type 1 times Avogadro constant. In kinetics, we sometimes write concentration this way. This is the concentration of type 1 multiplied by Avogadro constant. Similarly, N2 over V, the number density for type 2, is the concentration of type 2 multiplied by Avogadro constant. So we can rewrite this equation for reaction rate. This is the concentration of 1 times Avogadro constant. This is the concentration of 2 times the Avogadro constant. And that's why we have another expression over here, F. I copied F, the exponential function here, the relative speed here, the collisional cross-section area here. The number density is the concentration of 1 times Avogadro constant. The number density of type 2 is the concentration of type 2 times Avogadro constant. Again, the collisional theory allows us to predict the reaction rate between type 1 particles and type 2 particles. Its reaction rate equals the orientation factor, the energy factor, and then the collisional frequency per unit volume. And it can be expanded this way. Now for elementary bimolecular reactions between type 1 and type 2, we learned another expression for the reaction rate. R, the reaction rate, is simply K times the concentration of 1 and the concentration of type 2. So this is a simple equation we have learned in general chemistry. K is the rate constant. Using Arrhenius equation, K is A, the pre-exponential factor, times the energy factor, e to the power of negative activation energy over RT. So the reaction rate is simply the pre-exponential factor in the rate constant multiplied by this energy factor, all right, in the form of an exponential function times the concentration of 1 times the concentration of 2. And look, we have two equations for a reaction rate. Over here, that's from collisional theory, and over here from general chemistry. I will just put an equal sign between this and this. So over here we have the reaction for reaction rate. On the left, orientation factor, energy factor, average relative speed, collisional cross-section area, concentrations of 1 and 2, Avogadro constant squared. On the right hand side, the pre-exponential factor, the energy factor, the concentrations of 1 and 2. Of course, we can just cancel the exponential function left and right, the concentrations of 1 and 2 left and right, and now we obtain the pre-exponential factor A. It's the orientation factor times the average relative speed times the collisional cross-section area pi d squared multiplied by the Avogadro constant squared. So A is proportional to F, it's proportional to the relative speed, it's proportional to the collisional cross-section area. So A implicitly includes the entropic effect that's embedded in this F, the orientation factor.